Okay, my name is John Helveston, and this is an introduction to MAOpy, which stands for Monotonicity Analysis and Optimization in Python. This is a program I built in Python, and before I get into describing and showing you the software, I'm going to give a quick overview of optimization and monotonicity analysis. So in general, in optimization, what you're trying to do is identify the values of some variable that minimize some function. So in this example, what values of x will return the minimum value for x squared. And if we just plot it, you can see that the solution is obviously where x is 0. So at that value, f of x is at its minimum. Now, sometimes you might have a problem, even a simple problem like this, where you say f of x is just a line equal to x, and the solution is at negative infinity, because you can always just keep getting a lower and lower value by reducing x. And this is not a well-bounded problem. So oftentimes in optimization, one of the first things you want to do is check if your problem is well-bounded. So in this case, it's not, and a lot of times we add a constraint to make it a well-bounded problem. So if, for example, in this case, if the x referred to maybe some physical thing like the length of a beam or something like that, then it would be an obvious constraint that x has to be greater than 0 because you can't have a negative length. So if we add that constraint, here I'm showing it in negative null form where negative x is less than or equal to 0, now this problem is well bounded. So all of the values where x is less than 0 are no longer feasible, and the solution is now where these lines intersect. And so it's at x equals 0. So this inequality becomes an equality, and we call this an active constraint. So this means that the solution is at the boundary of the constraint. Now, we can identify whether constraints are active or not in a problem by looking at the monotonicity of the functions in the problem. So for example, if we look at, in this case, the f of x is monotonically increasing. This just means that as you increase the value of x, the value of f of x will also increase. And likewise, if you decrease it, it will decrease. The g function here, the inequality constraint, is monotonically decreasing, meaning if you increase x, the value of g of x continues to get lower. And as a result, because these values are opposite, this means that the g constraint is going to be active because it's going to bind the objective function. And so this is actually generalizable. This is known as the first monotonicity principle. It states that in a well-constrained objective function, every increasing variable is bounded below by at least one active constraint. And likewise, any decreasing variable is bounded above by at least one active constraint. So this means that we can identify these constraints as already being active. In that case, we convert it to an equality rather than an inequality, and we can substitute the solution directly into the objective function. So for a very simple problem, you can actually solve the entire problem by just examining the monotonicity of the functions. Now, if it is a more complicated problem, it may not be as obvious. For example, if we were designing a pressure vessel, say, for example, we have an objective to minimize the material volume in the design of this pressure vessel. Well, we can do that using optimization. So this diagram here shows the cross-section of a pressure vessel, and there's 4 main dimensions that you would, as a designer, need to choose. Now, the material volume is this function here, f of x, and it looks really messy and complicated, but that is just describing the material volume based on these 4 dimensions. And we want to minimize that with respect to all the x's. Now this here that says x's belongs to p, this just means that it has to be positive values. You cannot have a negative dimension. Now there's a lot of constraints in this problem. In fact, there's 6 of them. Now these are all inequality constraints, but these exist for engineering purposes. So when you're designing a pressure vessel, there's some obvious physical limits that the pressure vessel must adhere to, otherwise it might not work and it might fail. So designers will add these constraints just for physical reasons. Now if we go through a full monotonicity analysis, it takes some time, but you basically you have to look at the direction of the monotonicity direction of each function in the problem. So we have 7 functions here, and they're all monotonic in all of the variables. So that enables us to do that. Now I'm not going to show you the entire process, but it's just basically identifying the positive and negative signs to identify whether the constraints are active. I've already done it, so the result is that actually these 4 constraints are active constraints. So we can set those as equalities rather than inequalities. And if we rearrange them, now that we've got them equal to 0, we can solve for the variables at the solution. And if we rearrange further and do some more substitution, a lot of substitution, we can finally get we can actually get the full answer. So here we've now solved the problem by just examining the monotonicity of the functions. And so now the optimizer, the minimizer, the 4 values of x1, 2, 3, and 4 that will minimize the volume can be given as a direct closed form expression of the parameters from the constraints. You can finally substitute all this back into the objective function and get the objective function also as a function of just the parameters. So this process is very powerful. Even if it doesn't yield a closed form solution, it does help you identify the active constraints before you begin doing any type of numerical optimization, and it might really help simplify your problem. So using monotonicity analysis as a first run, if your functions are nice and monotonic, this can be a very useful way to examine a problem and get some insight about it. Now I'm going to show you how I do the same thing, but using the software I built called MAOpy. Okay, so I've started up the MAOpy program here. This is written in Python, and you can see over here, here's the code. But basically, when you start up, it goes to this About page, and it just shows you some basic information about the program and a couple quick instructions on how to use it. So you want to go to the Inputs tab here and get started by inputting your information about the optimization problem that you have. So here's where you're going to enter your variables, parameters, objective function, and any constraint functions that you have. You'll see here it gives you information about the input format. So there's a specific format that you need to follow when you're inputting your information. First of all, any functions, like your constraint functions, need to be in negative null form. So these need to be, all of these values are less than or equal to 0. So that's how you need to write this here. You need to use math of the way that Python would read math. So if you wanted to say x squared, you wouldn't want to type in something like this, because this is x XOR 2 in Python. You would want to write star star 2, because that means raised to the power of 2 in Python. But otherwise, it's pretty straightforward. So if you input anything incorrectly and you hit run, it will just pop up an error. So the errors are going to show up here before you allows you to go further in the analysis to make sure that you've formatted everything correctly. Now, just so we have something that will run so I can show you the rest of the program, I have the example problem I just showed you already formatted up, so I'll just copy and paste these in. So if you remember, this was the pressure vessel, and we're trying to minimize the amount of material volume in designing this pressure vessel. So here are some simple bounds. All these parameters need to be greater than 0 and less than some of these upper bounds that I'm providing. And my parameters, there's 6 main parameters. These are just constants, and I can provide it a starting value, and if I leave them blank like this, it'll just assign it a starting value of 0.1 by default. But I'm going to use all these numbers for now. These are just appropriate numbers for a pressure vessel. The objective function is this long, nasty equation. If you remember, I just pulled this straight from the slides I just showed you. And here are my 6 constraints. These are engineering constraints. Okay, so if I hit run, you'll see what it does. It takes a few seconds, but basically it identifies the active constraints, and then if they are active, it substitutes those values back into the objective function. Okay, so here it's identified that there are 4 active constraints. You remember these over here These are in negative null form, so these are inequalities. This is that this value is less than or equal to 0. Because it's active, it now sets them equal to 0, and then makes a bunch of substitutions so that you can find the variables x1, 2, 3, and 4 as a function of your constants, just a bunch of different parameters. And then substitutes these in, and now you have your objective function at the solution. So this is nice. It's a closed form, nice expression of the whole problem, and you've actually solved the whole problem. Now there's a few more things I can do with this program. Is I can analyze which of these parameters are really big drivers in driving the objective function value. So how sensitive is the objective function value to each of my parameters? So if I click on sensitivity, I can examine that. And what you see is it shows you the objective function value evaluated at this value for each parameter. So here are all the different parameters. It starts at the values that I gave it. So over here in the inputs, these starting values, that's all it's doing. If you give it a constant, a number, it's just going to assign it here. And then you have these upper and lower bounds, and these are set by just 25% upper or lower from the current value. So I can slide this and see how the objective function value changes, and I can see that the result is pretty sensitive to this vmin parameter. Maybe some other ones, lmin, it's not sensitive at all. It doesn't change it at all. Tmin, it changes it a little bit here. Okay, so you can kind of get a very quick look at how sensitive these parameters are. You can also change these. So if I was considering design options between maybe 20 and 48, these are my bounds I was considering. If I update my slider bounds, now I can go all the way up to those values. All right, so you can assign these to whatever you want as the designer. Okay, and then finally, if I want to look at visualizing this information, I can just add these, click these plots and look at it. So here, the plot f of x versus parameters. This is just going to show me how this objective function value changes as I change my parameter value. So this is the vmin, and you can see that it's pretty sensitive to it. The value changes a lot as I change vmin. I can look at any number of these, and if I want to just look at all of them here, just to show you, now I can really get a sense as which of these parameters are really driving the result. So it looks like vmin and lmax are really important for the objective function value. Amin is slightly also pretty important, but these other ones are not really too sensitive. It's not really sensitive to these. Finally, you can also do make a tornado graph. The name comes from the shape. It kind of looks like a tornado, and all this is another way of visualizing the same information. So you'll see that the parameter values I have here for the lower bound, upper bound, and the current value, that's what you're seeing here. So the objective function value, as you change the vmin, the objective function value changes a lot, but as you change these other ones, it doesn't change very much at all. So you can just get a really quick sense as to which of these parameters is really driving your result. Okay, so that's MAOpy. Right now, the program only works if you use fully monotonic functions. So the objective function and the constraints all have to be monotonic. If there's any non-monotonicity there, it will not work. But that is the current version. In the future, I will enable this to give you a regional analysis based on multiple on non-monotonic functions. So that is all I have. Thank you very much.